All right, welcome to your Calculus 2 class. I'm telling you guys, we're gonna have some fun here. First thing I want to ask you is, did you watch the video I sent you about how to enter learning mode? Okay, if you haven't, please do so. If you have, then continue. So what I want you to do is to prepare every time you go to a lecture, watch a video, study, or anything. Please be aware, use mindfulness, and get into that learning mode. Okay? All right, now, what I want you to do is pause the video while you take 3 deep breaths. While you take those 3 deep breaths, think about 2 positive affirmations about yourself. I mean, anything that you think you're good at, like, I don't know, I'm such a good son or daughter, or I love myself, that's valid. What else? Sorry, I'm so good at my workouts, or maybe I should say I work out so well. Whatever. Well, any 2 things that are positive about yourself. So please do that. Enter your start learning mode, and then continue watching the video for the Reimann Sums. All right, let's start with the Reimann Sums. Why I start here? This is Calc 1. This is a review of Reimann Sums. Well, it just happens that the concept we use to do Reimann Sums, or to find the definite integral in Calc 1, is the same concept we're going to use a lot in Calc 2. With that concept, we do volumes of solids of revolution, we do find lengths of curves, and many more things. It's used all over the place. So by understanding this concept now, you're going to understand a lot better your Calc 2. That's why I start here. So do you remember anything about your Reimann sums? Let's see. First thing we do about Reimann sums is understand what is a partition of an interval. So suppose you have an interval AB. A partition is just break down that interval into pieces, okay? With Reimann sums, we work pieces that are all of the same length. So let's say we partition this like that into 4 pieces, okay? Then what we do is we give a name to each of these ticks. That's the partition going to be, okay? So what we do is name A to be the first one, x0. Then we name the next tick x1, the next one x2, x3, and the last one x4. So for n equals to 4, we partitioned the interval AB into 4 pieces, all of equal length. So suppose you have, I don't know, the interval, let's say 0, 12. And you do this partition. In the middle, you're going to have a 6. Here you're going to have a 3. And here a 9, right? So you partitioned the interval from 0 to 12 into 4 pieces, all of the same length. What is the length of each piece? Of course, that length is going to be 12 divided by 4, which is 3. Each piece here has length 3. Okay? In the general case of an interval going from A to B, suppose n equals 4 again, and we're going to partition the interval now AB into 4 equal length pieces. All right? So what we take is okay, the length, the complete length from A to B. What is that length? Let me use the highlighter. What's that length here? Well, let's suppose 0 is right here. You would have to take B minus A, right? That is the length of this interval. So if you were to partition the interval AB into 4 pieces, you have to take the length b minus a, and divide it by 4. And then you have divided into 4 pieces. Just like we did here. Only that because it starts at 0, it is just 12. 12 minus 0 over 4. Okay, so that's the first thing we have to understand. We're partitioning the interval into pieces, all of the same length. Okay, all right. Once that is clear, what's the idea of the definite interval? First of all, what's the definite interval? So the definite interval is the integral of the function taken with within a defined interval, like from a to b. Is not the antiderivative, which is a function whose derivative is the given function. No, here we're finding what is the area below this curve. So we're finding this area right here, okay? That area right there. That's what we want to find. And that's why this is called definite, because you're going on a defined interval. Let's say from 3 to 15 or whatever, okay? All right, how we do that? Well, the idea here is to partition the given interval into n pieces. Okay, let's see how the partition looks if I, instead of using 4, we use n. How does that look like? Let me erase, no, not that. Let me erase here. And instead of 4, let's use n. How would that look like? So the first number is going to be a, and the last one, which is just n, because we're partitioned into n parts, is going to be called xn. Okay, and then you would go x1, x2, and so on and so forth until you reach xn. Of course, you're going to have many more ticks. Okay, in general, a is x0, b is xn, and then you go here, this would be x1, x2, x3, and so on and so forth until you reach maybe here xk minus 1. This would be xk, and this would be xk plus 1 until you reach xn. So this is anything in the middle, okay? So a general part of the partition. Okay, what's the idea here? We want to find the area below the curve. So what we want to do, it's, well, I don't know, because this is a curve. I don't know how to find that area. If it was a straight line, that would be easy. That's just the area of that rectangle. If it was a straight line like that, it would be, a straight line like that, a constant function, that would be just the value of that constant function times the length b minus a. And we would get the area below the curve if it was constant. But this is a curve. It is not easy. Okay? And that's why we need calculus. And the idea is, take the partition between a to b and subdivide that into n pieces. Then we're going to consider rectangles. Right here, another rectangle, maybe here, another rectangle here. And you see, we're going to take the areas of all those rectangles from all the way here, the last rectangle being something here, and add them up to get an approximation of the area below the curve. You see? In order to do that, we're going to introduce another guy, which could be, if you are in this interval, it could be the left endpoint, the right endpoint, or the midpoint. For clarity, I'm going to use the midpoint. And we call this guy x1 dot. And that at that point, I'm going to look at the value of the function. Remember, the value of the function is the height here. This is f of x1 dot. Okay? And that the values of the function are the heights. Remember, any point like xk here, any point on the graph has coordinates xk, xk, f of xk. Yeah? like x, f of x is the graph of a function. All right, so we take this rectangle here, approximating the height by the height of the function at x1 dot. Then we do x2 dot here. Look, the 2 goes with the next one, the 2 there. And then go up to the function at x2 dot and draw the rectangle from there down here. And you keep on doing that. That would be x3 dot. Go up there and take the rectangle there. Okay, and keep on doing that. When you go to this one here, let's say we are here, xk, remember the k with the k here, xk dot, that would be the height, and we would be considering this rectangle. So we're gonna be filling up all this with rectangles. So the idea is add the areas of all those rectangles, and that would give us an approximation, approximately, because we're a little over here, a little under here, over, under, over. You see, it is an approximation, it's not the exact value. And here comes the calculus concept. The idea is let the length of each piece of the partition approach 0 by making n big enough. So the bigger the n, the closer the ticks have to be to each other, right? So the thinner the rectangles that we're using. And you let that approach 0. How? Using the limit. Okay, you let n approach infinity, and then the length, what? What's the length of each of these pieces? Let me grab the blue one. What's that length over there? That is always the same one, right? We divided the length of the interval by n to make all the pieces of the partition to have length b minus a over n. And as you can see, this is just a constant, right? That's a constant. So when you let n approach infinity, this is approaching 0. So the lengths of the pieces are getting shorter and shorter, so tiny that it's almost like the rectangles do not have any width. Okay? That's the idea. When you take the limit and you do that process, that's when you get the exact area below the curve. So you see, if I refine my partition and I start taking, it's gonna give it a little messy, rectangles that are thinner and thinner, like that, refining the partition, you see we have more extras, we have less extra and less under, less extra, less under. Now imagine you almost have no width. That's when you're taking the limit, and that is what makes us be able to find the area below the curve right here. Okay? How do we do that mathematically? Not very complicated, just find the area of each rectangle, add them up, because we have finitely many of them, we have n rectangles, add the n rectangles, and then you take the limit. So this is exactly the concept that's going to be used a lot in Cal 2. So you do something in a safe place. I mean, a safe place, a finite place, something, somewhere that someplace where you can do your thing, okay? You do it, in this case, in a finite context, okay? You have a partition of n pieces. And then you take n to go to infinity. You let n go to infinity, making those intervals small. So this is a technique we do everywhere in Cal 2. Go to a safe place, I mean a finite place, or a place where I know what to do. Call it n, and then let that n either go to 0, go to infinity, whatever it's needed. That's a technique that we're going to use based on this concept, okay? So now mathematically it's really easy, because if I zoom out here, one of the rectangles, the height here, let me use blue, the right here is xk dot, comma, f of xk dot, because that's the graph of the function, right? So the height here is f of x k dot. So the value of that midpoint, and take the corresponding rectangle right there. So what's the area of each rectangle? The area of a rectangle, height, f of x k dot, times width. Okay. Now let's talk a little bit about the width. Since every piece of the partition has the same length, we call this delta x. Okay, so we give it just that name. This length here is delta x. It's the same as this length here, that's also delta x. So this length here, or the base of this rectangle, we call it delta x. So this would be f of xk dot delta x, and that would be the area of one rectangle. Then, as I said, if we just do mathematically all that I said, we're done. Add them. Add the n rectangles. You agree we have n rectangles here, right? Add them. So the first one is f of x. Add them, sorry, not add the rectangles, add the areas of the rectangles. So not x0, it starts at 1, x1 dot delta x plus f of x2 dot delta x plus f of x3 dot delta x, and so on and so forth, until we reach the last one, which is x n dot delta x. Okay, it's better to write it in summation notation. Let's write it in summation notation. This is going to be the sum from k equals 1 to n of f of x k dot delta x. Okay, now you see, this is what I'm saying. You are in a safe place. You are taking a finite sum, so we're fine, no problem here. Only that this here is just an approximation of the area below the curve f. All right, so the area below the curve means the area between the curve and the x-axis. The x-axis right here. Okay, so that's just an approximation, and to get the final exact area below f, what you have to do is just take the limit as n approaches infinity, because as n approaches infinity, this length approaches 0, and those rectangles becomes almost with no widths. Okay, so take that, the limit of what? Of this, and put it in blue, summation from k equals 1 to n of xk dot delta x. And that's the Reimann sum. That is the number. This is the area, the exact area below the curve. Okay? Now we have notation for that. When you take an infinite sum like this one, you call it the integral. Okay? So this is going to be the limit of the sum is the integral. The integral from, and now you have to look, okay, it was defined from A to B. That's where we took the partition from. So it goes from A to B. Of this, what's that? Well, that's just a function. The width of those, of these little intervals is becoming nothing. So we can consider xk dot like it was any x. And then delta x is the difference. It has a little more minimum, but it is the variable with respect to which we're working. Okay, so that's how we get the integral, the definite integral using the Reimann sum. And then I think you know this is kind of the lower limit of integration, upper limit. This is the integration. You see, it is very, I don't know, I think it's very nice. Why the symbol? This symbol means an infinite sum, because if this is the sum, they just elongated it to make it infinite. And so this is an infinite sum, basically, all right, that you get by adding n areas and then taking the limit as the delta x approaches 0, okay? So this reads the integral from a to b of the function. And, well, I think that's about it. I hope you understand better the concept of Reimann sum. And, well, be aware of this. We're going to do this so many times in call 2. You're going to go to a safe place where things are finite, where things are, we know how to do things there. And then we're going to take a limit, okay, to make it infinite. Kind of the calculus idea behind all of these concepts. Sorry. All right, now here. I'm gonna try to link this to the YouTube video. I don't know if I'm gonna be able, but in any case, I'll send it to you. But this is a group of mathematicians that got together. Sal from Khan Academy is in there. It is a YouTube channel called 3 Blue 1 Brown, and that's because the guy has 3/4 of the eye blue and 1/4 brown. It's funny, but they are amazing. And, well, what's amazing about them is that you're not going to watch a video repeating what I told you. You're going to watch a video where they graphic everything. They explain it to you in real life, like with velocities and things that you are already familiar with. And the animations and the graphics they made themselves are amazing. So I really recommend you to watch this video and enjoy it, because it's really enjoyable. The work they display there is amazing. Okay, so bye. See you for the next video. Bye-bye.